Imagine you are driving an electric vehicle on the highway. You're just cruising along at a solid 70 miles per hour, feeling completely in control.
Right. The ride is smooth. The cabin is totally quiet.
Exactly. But what keeps that incredibly powerful electric motor under the hood from just suddenly locking up or, losing all of its torque in a split second?
Yeah. What prevents a catastrophic loss of control while you're literally hurtling down the asphalt?
Right. And the answer, well, it lies in a tiny component that is essentially the motor's sense of balance, the encoder. So, okay, let's unpack this.
Let's do it.
Because to understand how that safety is guaranteed for you, the driver, we are going to explore a really intense, highly technical specification document today. It's titled ASIL D Encoder Anomaly Analysis and Technical Specifications.
And for those tracking the industry standards, ASIL D represents the absolute highest automotive safety integrity level. I mean, it is the gold standard for preventing catastrophic failures in automotive engineering.
It really is. So our mission for this deep dive is to completely unpack how automotive engineers actually achieve this ASIL D standard. We'll explore, the physics of how things break, the clever software that catches errors in literally milliseconds, and, well, the extreme manufacturing and testing protocols that keep you safe.
And just to set the stage for you, our listener, the backdrop for today's deep dive is basically a digital schematic of an electric vehicle drivetrain. It really symbolizes the intersection of hardware and software we are about to explore.
Yeah, hardware and software. But before we look at how a system defends itself, we have to look at the physical reality of the environment it lives in, right?
Oh, absolutely. The physical environment is brutal.
Yeah. So in this technical specification, the root causes of encoder anomalies, they're broken down into 4 distinct physical dimensions.
Right. We are looking at the physics of failure here.
Yeah.
And the source starts with optical encoders.
Okay, so an optical encoder, it uses light to measure the rotation of the motor. You have this precision glass disc with microscopic slits and a light-emitting diode, an LED, shining through it to a photodetector.
Which sounds great in the lab.
Right, but if you are putting a delicate glass disc inside an electric motor housing, you're immediately dealing with the coefficient of thermal expansion.
Exactly. The housing is metal, the disc is glass.
Yeah, and they expand and contract at completely different rates when exposed to the extreme thermal shocks of a car. The spec actually mentions temperature swings from negative 40 degrees Celsius all the way up to positive 150 degrees Celsius.
And that differential in thermal expansion, it creates just immense mechanical stress.
I can imagine.
Yeah, and when you couple that rapid temperature cycling with the high-frequency random vibrations of a moving vehicle, which range from like 100 to 1,000 hertz, that delicate glass disc is highly susceptible to developing stress microcracks.
Wow, just from shaking and heating.
Right. And in extreme cases, it can shatter entirely. But, even if the glass survives, the optical system has a secondary vulnerability right at the semiconductor level.
Oh, you mean the LED itself?
Yeah. When the operating environment consistently exceeds 130 degrees Celsius, the LED suffers from thermal saturation.
Because the actual physics of the LEDs start breaking down. Since LEDs rely on the recombination of electrons and holes across a semiconductor band gap to emit photons.
Precisely. That's the mechanism.
So as the temperature spikes, the kinetic energy of those electrons increases, and, well, they are more likely to recombine non-radiatively, meaning they just generate heat instead of light.
Yeah, it becomes a vicious cycle.
So the luminous intensity, the actual brightness of the LED, it degrades over time.
And the result is this severely distorted pulse amplitude hitting the phototransistor. The receiving sensor isn't getting a clean on or off signal anymore.
It's just getting a weak wave.
Exactly, a weak erratic wave. And this leads to what the engineers call pulse loss or phase distortion.
And in a vehicle using field-oriented control, or FOC, this is a huge problem.
Well, it's a critical failure. The motor's power delivery becomes totally erratic.
Right, because the FOC algorithm, it completely relies on the precise rotor angle to calculate the mathematical transforms that govern the stator currents. If the angle is wrong, the magnetic fields are misaligned, and you get severe torque ripple.
Yeah, the car would essentially start jerking violently.
Because field-oriented control is entirely dependent on timing. It uses the Clark and Park mathematical transforms to take the three-phase alternating current and view it as a two-dimensional vector.
It's a brilliant piece of math.
It is. It essentially tricks the processor into controlling an EC motor as easily as a DC motor. But, those equations only work if you know the exact microsecond the rotor passes a specific point.
Right, garbage in, garbage out.
Exactly. If the encoder drops a pulse because of a cracked glass disc or a dim LED, the math instantly falls apart. So, why use optical encoders at all in such a hostile environment?
Well, the trade-off must be precision. But clearly, the vulnerability pushes engineers toward the second category, detailed in the source material, which is magnetic encoders.
Okay, so magnetic encoders, those are much more robust physically, right?
Oh, much more. They don't use fragile glass. They use a magnetic target wheel and a Hall effect, or magnetoresistive sensor.
But they introduce an entirely different set of vulnerabilities, don't they?
They do. The first one is thermal demagnetization.
Heat again?
Always heat. When an EV motor is under heavy load, the rotor and the magnetic target material can easily exceed that same 130 degrees Celsius threshold.
And as you approach the Curie temperature of the magnetic material, the thermal agitation of the atoms basically overwhelms the magnetic alignment of the domains.
Exactly. The magnetic field permanently weakens.
And once the signal amplitude drops below the detection threshold of the resolver to digital converter, the RDC chip, the system just goes blind.
It does. But, looking at the notes on electromagnetic interference, EMI, that seems to be the much larger threat to magnetic encoders.
Oh, definitely. Because inside a modern dual-motor powertrain, you have this very compact, space-housing, high-voltage silicon carbide, or SiC MOSFETs.
And those transistors are chosen specifically because their wide bandgap allows them to switch massive amounts of power on and off at incredibly high frequencies.
Right, which vastly improves the motor's efficiency.
It does, but that rapid switching is actually the core of the problem. We are talking about voltage changes, the dV/dt rate of greater than 10 kilovolts per microsecond.
That is absurdly fast.
It is. And when you shift electrical energy that violently, you generate massive high-frequency common mode and differential mode noise.
Okay, let me break down those noise types really quick because they act differently. Differential mode noise is when the interference travels down one wire and returns on the other, just like a normal signal. It actively fights the intended data.
Right.
But common mode noise is when the interference spikes on both wires simultaneously relative to the ground. And at these switching frequencies, you run into parasitic capacitance.
That is the crucial mechanism right there. Normally, the insulation around a wire stops electrical current. We all know that.
Sure.
But at extremely high frequencies, the physical space between two adjacent conductors actually acts like a capacitor.
Oh, wow.
Yeah, as the frequency of the noise increases, the impedance of that parasitic capacitor drops.
Meaning the high-frequency common mode noise from the high-voltage silicon carbide switching just punches right through the insulation.
Exactly. It couples directly into the low-voltage signal wires of the encoder.
It's like, okay, imagine trying to read a book with a tiny flashlight while someone next to you is blasting a massive high-intensity strobe light at random intervals.
That's a perfect analogy.
Right. The strobe light is the EMI from the transistors. The flashlight is your magnetic encoder signal. The signal is completely drowned out, which causes the RDC chip to register these erratic voltage spikes as actual encoder pulses.
And the system registers these false pulses and instantly miscalculates the speed.
Which triggers a false overspeed alarm.
Right. It panics because the electrical noise is mimicking a motor spinning out of control.
That's terrifying. So if we move from the physics of heat and noise into the digital realm, the technical specification details the third root cause, which is metastability.
Metastability. This occurs when you have two different systems trying to communicate, but they are running on slightly different clock domains.
Like they're out of sync.
Exactly. The RDC chip, like the AD2S1210 mentioned in the source, is generating simulated encoder pulses based on its own internal oscillator.
Meanwhile, the main microcontroller unit, the MCU, is trying to read that data over a serial peripheral interface, an SPI bus, using a completely separate clock.
And because the clocks are unsynchronized, the phase between them is constantly sliding back and forth.
And the critical failure happens at the transistor level, inside the digital registers.
Yes. Every flip-flop circuit requires the incoming data to be stable for a specific amount of time before the clock triggers.
That's the setup time.
Right. and it must remain stable for a specific time after the trigger.
The whole time.
Exactly.
So if the MCU clock triggers the register to read the data at the exact nanosecond, the RDC chip is transitioning the voltage from a 0 to a 1. You violate that setup and hold time.
The physical transistors in the flip-flop basically get caught halfway between their threshold voltages?
The register gets trapped in a metastable state. It's like this intermediate voltage level that eventually resolves randomly to either a 0 or a 1, just as thermal noise pushes it off balance.
And when it resolves to the wrong value, you get a random, physically impossible angle jump.
Wow.
The system suddenly registers that the motor rotor has instantly teleported to a completely different rotational position.
Which triggers a loss of tracking error and immediately crashes the control algorithm.
All because of a timing mismatch measured in picoseconds.
A literal digital hallucination caused by unsynced oscillators. That is wild. And that takes us to the fourth root cause, which actually brings us right back to the physical degradation of the hardware.
Right, fretting wear.
Fretting wear on the low-voltage connector pins. The spec mentions that the constant high-frequency vibration of the car causes these pins to experience microslip of less than or equal to 5 micrometers.
Just tiny, tiny movements. And to understand the damage of a 5-micrometer slip,
Yeah.
you have to look at the chemistry of the connector.
Okay, let's look at it.
These pins are typically copper, coated in a protective layer of tin. The microscopic rubbing, it acts like sandpaper. Yeah, it slowly scrapes off the tin plating, exposing the oxygen-free copper underneath.
And as soon as that pure copper is exposed to the air, it vigorously oxidizes. It builds up a layer of copper oxide and tin oxide, both of which are essentially insulators.
Right, they block electricity.
So the constant vibration essentially creates microscopic cold welds at the peaks of the metal surfaces, which then fracture, exposing more metal to oxidation.
It just builds up a thicker and thicker insulating layer, right where the electrical connection needs to be the absolute strongest.
But so what does that do to the resistance?
The electrical resistance of that connection spikes from a healthy state of under 5 milliamps to over 100 milliamps.
That's a massive jump.
It is. This jump in resistance severely attenuates the electrical signal, causing microsecond-level signal dropouts. The angle feedback is lost, and the system instantly loses driving power.
So the electrical signal is literally slowly choked to death by microscopic chafing.
Basically, yeah.
I mean, let's summarize this. We have glass shattering from thermal shock, magnets losing their fields, massive electromagnetic noise punching through wire insulation, mismatched digital clocks causing random hallucinations, and fretting wear oxidizing the physical connections.
The physical layer is fundamentally vulnerable.
Very. So if we accept that these physical failures are just inevitable over the lifespan of a vehicle, the system must have an architecture designed to detect and manage these failures before the driver loses control.
And that requires a transition into the second part of the spec, the software and hardware co-diagnostics architecture.
The digital immune system.
Exactly. The entire goal of this architecture, which is mandated by the ASIL D standard, is to identify and react to a fault within a strict fault-tolerant time interval.
The FTTI.
Yes, an FTTI of less than or equal to 60 milliseconds.
60 milliseconds. In that microscopic window, the car has to realize a sensor broke, figure out a backup plan, and actually execute it.
It's incredibly fast. And the first line of defense is hardware pulse diagnostics.
Okay.
The microcontroller's hardware timers are constantly running a plausibility check on the signals. For optical and magnetic encoders, the A and B signal pulses must strictly maintain a 90-degree phase difference, which is known as quadrature.
The 90-degree offset is fundamental, because if signal A and signal B were perfectly in sync, the computer would only know the speed of the motor.
Right, would know the direction.
Exactly. By offsetting them by 90 degrees, the computer looks at which signal goes high first. If signal A rises while signal B is still low, the motor is spinning forward.
And if signal B rises while signal A is still low, the motor is in reverse.
Right. So the hardware timer is constantly watching the edge transitions of these square waves. If that phase difference deviates from 90 degrees, or if both signals transition at the exact same time, which is physically impossible in a quadrature setup, the hardware timer instantly flags a hardware fault.
Furthermore, for systems using sine and cosine magnetic sensors, they utilize dual analog-to-digital converters, or ADCs.
2 of them.
Right. These dual ADCs monitor the sine and cosine signals synchronously. If the phase or amplitude deviates mathematically between the two channels, it immediately flags a sampling anomaly.
But, those hardware checks only verify the electrical integrity of the signal?
Yes.
What happens if the hardware seems fine, like the pulses are 90 degrees apart, the voltage is correct, but the actual positional data is subtly corrupted by EMI or a mechanical slip?
That requires a higher level of verification, which leads us to the software-level doer-checker system.
Right.
This is an implementation of heterogeneous computing, and it is a critical distinction. They don't just run the same software on two cores to see if they match, which is known as lockstep computing.
Because lockstep would catch a random cosmic ray flipping a bit in a processor, but it wouldn't catch a systemic error in the logic itself, right?
Exactly. The doer-checker architecture runs different algorithms on completely different inputs to arrive at the same truth.
Okay, so you have the main core, the doer. It runs the highly optimized, dynamic, field-oriented control loop, spinning the motor based directly on the encoder's data.
Right.
But the secondary core, the checker, completely ignores the encoder. Instead, it looks at the raw electrical current and voltage being fed into the motor's stator.
It runs a complex mathematical model called a Model Reference Adaptive System, or MRAS.
MRAS?
Yeah. The MRAS utilizes two models simultaneously. It has a reference model, which uses the measurable stator voltage and current to calculate the magnetic flux. Then it has an adaptive model, which estimates the rotor's position based on back electromotive force, or back EMF. The algorithm calculates the error between these two models and uses a proportional integral controller to force the estimated angle to converge on the true angle.
So basically, the doer is navigating based on the GPS, the physical encoder,
Right.
and the checker is sitting in the passenger side, completely ignoring the GPS and calculating their exact position based purely on the physics of magnetic flux conservation and back EMF.
That's a great way to picture it. And the system constantly compares the encoder's reported angle against the checker's mathematically predicted angle.
And the specification notes that if those two angles deviate by more than a calibrated limit, specifically greater than 10 degrees, it means the encoder data is fundamentally flawed.
Yes, and when that deviation occurs, the safety core bypasses the main control software entirely and triggers a hard shutoff in under 100 microseconds.
Wow. But wait, is there a risk of oversensitivity here? I mean, we discussed the massive electromagnetic noise generated by the silicon carbide transistors earlier.
There is a huge risk, actually.
Right, because if the encoder experiences a tiny 1 microsecond glitch because of a stray burst of common mode noise, you don't want the vehicle to violently shut down on the highway.
Exactly. A false positive triggered by an electrical hiccup could be just as dangerous as a real mechanical failure.
So how do they prevent this overdefense?
The software employs a time domain sliding debounce window of 3 milliseconds.
Okay, so a 3 millisecond delay.
Sort of. If there is a sudden angle jump or a pulse loss, it doesn't instantly panic. During that 3 millisecond window, the software actually uses a prediction model.
Oh, like it guesses where it should be.
Yes, it looks at the historical speed and acceleration of the motor and performs a second-order extrapolation to guess where the angle should be.
It essentially uses a Taylor series approximation to mathematically substitute the missing hardware data based on the motor's last known trajectory.
Exactly. The software interpolates the gap.
But if that 3 millisecond window expires and the interference is still present,
Then the system confirms it is a real, persistent fault, not just a transient noise spike. And at that exact moment, the adaptive fallback protection matrix is triggered.
okay, so this matrix is how the vehicle dynamically reacts based on the severity of the situation and the current speed.
Right.
The first level is a soft fallback. The system completely ignores the broken physical encoder and switches on the fly within 5 milliseconds to a sensorless control mode.
It relies entirely on the mathematical MRAS observer model we just talked about.
But driving purely on math is less precise than using a high-resolution physical sensor, especially at low speeds, isn't it?
It is. The limitation at low speeds is actually crucial. The MRAS relies on back electromotive force to calculate the rotor angle.
And back EMF is the voltage generated by the motor spinning through its own magnetic field.
Exactly. So at very low speeds, the back EMF signal is incredibly weak, often getting totally lost in the baseline electrical noise of the inverter.
Which is why the soft fallback puts the car into a limp home mode. It limits the maximum torque to 30% and caps the speed at 3,000 RPM, equating to roughly 40 kilometers per hour.
By restricting the torque and speed, it prevents the motor from overheating or suffering magnetic saturation due to slight calculation errors.
Allowing the driver to safely pull over.
Right. But that fallback is only viable if the failure happens at a moderate speed.
What if you're doing 80 miles an hour on the highway?
Well, with the motor spinning over 7,200 RPM, switching to sensorless control might not be stable enough to manage the immense rotational energy.
You also face the danger of the motor itself. I mean, a spinning electric motor is inherently a generator.
Oh, exactly. If a catastrophic sensor failure occurs at high speed, you cannot just open the circuits and let the motor freewheel.
Right, because if you disconnect the inverter and let a high-speed motor spin freely, the permanent magnets in the rotor will generate an uncontrollable, massive back EMF voltage spike.
And that voltage spike will flow backward from the stator coils directly into the inverter.
It will easily exceed the breakdown voltage of the silicon carbide components, literally destroying the power electronics.
Yes, the car would essentially fry itself.
So to prevent this overvoltage destruction, the system abandons the goal of keeping the car driving and focuses entirely on protecting the electrical architecture.
It executes a stepwise active short circuit, or stepwise ASC. This is the hard fallback.
So wait, short-circuiting the motor on purpose? That sounds incredibly dangerous. Why is that the safe option?
Because short-circuiting the stator coils intentionally forces the generated electrical energy to loop harmlessly inside the motor's own windings rather than spiking back into the delicate electronics.
Oh, I see.
Yeah, the magnetic field created by the short-circuited current actually opposes the rotation of the rotor, acting as a massive electromagnetic brake.
But if you instantly slam all three phases into a short circuit at 12,000 RPM, the sudden negative torque, the physical braking force, would be so violent it could mechanically shear the drive shafts.
Or cause an immediate loss of vehicle traction. You'd spin out.
That is why it must be a stepwise process.
Exactly. Phase 1 lasts for precisely 1.5 milliseconds. The system executes a two-phase short circuit based on the last known rotor angle,
Which creates an asymmetrical magnetic field that allows some of the transient current shock to dissipate into the rotor's squirrel cage or magnets, absorbing the initial spike.
Then, in Phase 2, it transitions into a full three-phase lower bridge short circuit.
And this creates a symmetrical, steady braking torque that safely decelerates the motor and successfully clamps the DC bus voltage to under 720 volts, ensuring the inverter and the high-voltage battery actually survive the event.
The choreography of that sequence is staggering when you think about it.
It really is. I mean, you have a microscopic loss of contact due to fretting wear.
Right.
The hardware timer flags a quadrature violation.
Yep.
The doer checker flags a 10-degree MRAS deviation. The 3-millisecond sliding window confirms it isn't just noise.
And then the fallback matrix calculates the speed is too high for sensorless control and dynamically executes a precisely timed two-step short circuit to electromagnetically brake the vehicle without frying the transistors.
All within 60 milliseconds.
That's mind-blowing.
But, you know, as brilliant as that software net is, it's still just treating the symptom, right?
It is.
Catching an error quickly is great, but why not design a system where the error physically cannot occur in the first place?
And this brings us to the core of the ASIL D philosophy, which is part 3 of the document, DFMEA.
Design failure mode and effects analysis.
Right. How do engineers alter the physical blueprint of the vehicle to eradicate these failure paths entirely?
Well, they utilize strict, unyielding design mandates that lock the bill of materials. Like, the specification explicitly dictates the architecture of the analog front-end filter circuits.
These are the circuits designed to clean up the analog signals before they hit the analog to digital converters.
And the mandate requires the exclusive use of Class 1 CRG, also known as NP0, multi-layer ceramic capacitors.
And the choice of that specific dielectric material is entirely about thermal stability. We talked about the thermal shock earlier, going from -40 to positive 150 degrees Celsius.
Right. Normal Class 2 or Class 3 capacitors like X7R or Y5V, they use barium titanate dielectrics.
And when those get hot or cold, their capacitance value drifts wildly.
Yeah. And if your filter's capacitance changes, the cutoff frequency of your low-pass filter shifts, meaning high-frequency noise, suddenly gets through to the processor.
But Class 1 CRG capacitors do not use barium titanate. They use a temperature-compensating ceramic dielectric that is incredibly stable.
They have a temperature coefficient of essentially 0, right?
Specifically 0 plus or minus 30 parts per million per degree Celsius across the entire extreme temperature range.
Their thermal drift is virtually non-existent.
And, on top of that, that specific material has zero piezoelectric effect.
Right, because certain ceramic capacitors exhibit piezoelectricity, meaning if you physically vibrate them, the mechanical stress generates a tiny electrical voltage across the terminals.
Exactly. In a vibrating car, normal capacitors act like tiny microphones.
Turning the engine's mechanical vibration into electrical static, introducing microphonic noise right into the sensor lines.
But by locking the Class 1 C0G capacitor into the blueprint, engineers mathematically remove the vulnerability to heat and vibration at the component level.
That's incredible. So what is the next design mandate to eliminate the metascalability issue we discussed?
Synced clocks. To eliminate the digital hallucination caused by mismatched timing between the RDC chip and the MCU, the hardware design rules now dictate that both components must share a single, high-precision hardware clock source.
Oh, so by tying both the decoding chip and the main microcontroller to the exact same crystal oscillator, you eliminate the phase sliding.
Exactly. The specification notes this keeps the phase error to less than 0.5 degrees.
If the clocks are locked together, the MCU will physically never attempt to read the register at the exact nanosecond the RDC is transitioning the voltage.
The setup and hold time violations are just architecturally removed.
Here's where it gets really interesting, though. The third design mandate deals with something that sounds like it belongs in aerospace engineering, not automotive.
Oh, you mean the cosmic rays.
Yes. Hardware ECC and BGCRC to protect against single-event upsets caused by cosmic rays. Wait, you're telling me outer space radiation can actually cause a motor to stall out on the freeway if we don't put ECC memory inside the car?
I am. High-energy neutrons generated by cosmic rays striking the atmosphere, they are constantly passing through the Earth and through everything on it.
Including cars.
Right. If one of these high-energy particles happens to strike a memory cell inside the car's microcontroller SRAM, the kinetic energy of the impact can release a burst of electrical charge within the silicon.
And if that burst of charge is large enough, it can overcome the capacitance of the memory cell, physically flipping a bit of data from a 0 to a 1 or a 1 to a 0.
Exactly. If a cosmic ray flips a critical bit in the memory register holding the rotor angle data, the FOC algorithm would instantly calculate the wrong magnetic vectors, potentially stalling the motor.
That is insane. To prevent this, ASIL D mandates CCDID, single error correction, dual error detection memory architecture.
Right. This involves a hardware-level error correction code, or ECC, running alongside a background cyclic redundancy check, a BGCRC.
The architecture doesn't just store the data bits, it calculates and stores extra parity bits using Hamming codes.
Hamming codes are just brilliant.
They really are. They arrange the parity bits so they cover overlapping subsets of the actual data bits. If a cosmic ray flips a single bit, the hardware calculates the parity again, and the specific combination of parity errors will mathematically point to the exact intersecting location of the corrupted bit.
And then the ECC hardware can silently flip it back.
Autocorrecting it in less than 1 millisecond. Without the main software ever even knowing a cosmic ray struck the car, it acts as an invisible background checksum.
And the dual error detection aspect means that if a massive radiation strike manages to flip 2 bits simultaneously within the same word, the overlapping parity bits will flag an uncorrectable state,
allowing the system to instantly trigger a safe fallback rather than acting on corrupted data.
Right. Now, the final key design mandate addresses the massive electromagnetic interference from the silicon carbide transistors. Symmetrical shielding.
The specification requires high-density twisted cables with a braided shield coverage of 85% or greater.
Twisting the signal wires ensures that any external electromagnetic field induces an equal but opposite voltage in each wire,
causing the differential mode noise to cancel itself out. But shielding against the high-frequency common mode noise requires specific grounding techniques. The spec demands 360-degree circular metal backshells.
It strictly forbids the use of a pigtail ground connection.
A pigtail is when a manufacturer takes the braided metal shield, twists it into a single wire, and smooths it into a ground point, right?
Yeah. It is cheap and easy to assemble. However, at the high frequencies generated by silicon carbide switching, a pigtail has significant parasitic inductance.
At 10 kilovolts per microsecond switching speeds, the impedance of that tiny pigtail wire becomes incredibly high. The shield is no longer effectively grounded at those frequencies.
Instead of shunting the common mode noise to ground, The pigtail actually acts as an antenna, radiating the noise right into the sensitive inner wires.
By mandating a 360-degree clamping connection with a grounding resistance of less than 10 milliams, the design maintains a continuous low-impedance Faraday cage around the signal wires.
Completely blocking the capacitive coupling of the noise.
Okay, so we have mathematically stable capacitors, perfectly synced hardware oscillators, radiation-hardened memory architecture, and flawless 360-degree electromagnetic armor.
The DFMEA ensures the blueprint is invincible.
But a perfect blueprint is theoretical, right? We must now transition to the physical reality of the factory floor.
The fourth section.
Right, part 4. How do engineers ensure that a factory worker or an automated machine actually builds this 360-degree shielded cable without accidentally leaving a millimeter gap or without improperly crimping a wire?
Well, that transition from design to manufacturing introduces PFMEA, or process failure mode and effects analysis. The goal is to basically bulletproof the assembly line.
Modern automotive manufacturing at the ASIL D level relies heavily on the Japanese concept of poka-yoke, which translates to mistake-proofing.
You design the assembly process so that it is physically impossible for an error to proceed to the next station.
Take the microscopic fretting wear we discussed earlier, the 5 micrometers of vibration rubbing the tin off the pins and exposing the copper to oxidation. The design solution is to lubricate the pins to block the oxygen.
But how do you mistake-proof the application of grease inside a microscopic connector?
Yeah, how?
They utilize automated microgreasing combined with automated optical inspection, or AOI. A precision robotic dispenser injects an incredibly exact volume of a specific automotive-grade fluorosilicone grease.
The specification mandates Niogel 760G, right?
Right. Fluorosilicone is chosen because it has immense chemical stability and doesn't degrade under high temperatures, maintaining a protective physical barrier over the copper, even if the tin is abraded away.
But the genius of the poka-yoke system here is the tracer. The grease is manufactured with a UV fluorescent additive.
It's so smart. After the robotic arm injects the grease, the connector moves under the AOI camera, which blasts the pins with high-intensity ultraviolet light.
It's like forensic science on the assembly line.
It really is. The camera's image recognition software must visually confirm a 100% perfect glowing pattern of grease on every single pin.
While also verifying there is no spillage that could bridge 2 pins and cause a short circuit.
Exactly. If the camera detects a shadow or an imperfect shape, the automated system physically locks the assembly jig. The part literally cannot be removed or passed down the line until a supervisor clears the fault.
Machine vision guarantees the chemistry is applied perfectly. Another physical connection vulnerability is the crimping of the metal terminals to the wires. If a crimp is too loose, the wire can pull out or suffer high contact resistance.
And if it's too tight, the mechanical deformation can break the internal copper strands.
So the process controls utilize dynamic crimp monitoring.
The crimping presses are equipped with precision force and displacement sensors. As the die compresses the metal terminal around the wire, the sensors plot a physical force curve in real time.
Mapping exactly how much force is required at every millimeter of the stroke. It is utilizing Hooke's law and the plastic deformation properties of the metal.
Right. Every specific terminal and wire combination has an ideal force displacement signature.
And if the curve deviates by a fraction of a percent, meaning maybe a single strand of copper wire is missing or the insulation wasn't stripped back far enough, the press immediately halts.
And the factory doesn't just trust the digital curve. The specification demands a physical destructive pull test every single shift,
proving that a completed crimp can withstand a minimum of 50 newtons of force before failing.
The power connections also require extreme process controls. For the high current bus bars, the enemy is joule heating.
Right. If a bolt isn't tightened to the exact specification, or if the wrong metallic coating is on the bolt, the contact resistance rises.
And at the high currents required by an EV motor, even a few extra milliams of resistance will generate massive amounts of heat, potentially melting the connector.
To mistake-proof the tightening process, they use networked servo screwdrivers running a torque angle fastening algorithm. The screwdriver doesn't just stop at a specific torque, it monitors the exact angle of rotation required to achieve that torque,
ensuring the bolt hasn't cross-threaded or stretched plastically.
But the process starts before the tool is even engaged, right? An optical character recognition, or OCR, camera is positioned over the assembly station.
The OCR system reads the packaging of the bolts the worker is picking up. It verifies they're using bolts marked as phosphate-coated, which the engineering blueprint dictates to ensure the final contact resistance remains under 5 milliamps.
So what happens if a worker tries to manually override the torque screwdriver? Like just ignores the camera?
The worker physically cannot override this.
Huh.
The servo screwdriver will remain electronically disabled until the OCR camera confirms the correct phosphate-coated bolt is in the tray.
Wow, a hard lockout.
Yes. And if the torque angle friction curve deviates during fastening, the servo registers a failure in the factory's central computer, known as the Manufacturing Execution System, or MES.
And if we connect this to the bigger picture, the MES tracks every single data point. The torque curve of every bolt, the UV camera image of every greased pin, the force curve of every crimp. It is all serialized and tied to the specific barcode of that individual motor.
The final, definitive validation of this process happens at the end of line, or EOL, testing station.
The EOL station is where the fully assembled motor is spun up for the first time. The system performs a rotor phase self-learning offset, or ROL.
The test bench spins the motor and uses highly accurate external sensors to measure the physical back electromotive force generated by the stator coils.
And by mapping the precise zero crossing point of the back EMF sine wave, the system pinpoints the exact physical magnetic 0-degree mark of the rotor.
It then compares that physical truth to the 0-degree mark reported by the freshly assembled encoder. It mathematically calculates the exact offset angle between the physical magnet and the digital sensor.
And permanently writes that calibration offset into the motor's control software.
And crucially, that specific ROL calibration data must be successfully uploaded directly to the MES cloud.
Right. If the physical measurements of the back EMF deviate from the mathematical model, indicating a slight misalignment during manufacturing, or if the data simply fails to upload to the server, the MES system initiates a hard lockout.
It literally refuses to print the shipping label. The factory physically cannot produce a bad part without triggering a system-wide halt. The data traceability is absolute.
That is just phenomenal. Which brings us to the fifth and final stage of the engineering life cycle. We have designed an invincible architecture on paper. We have built it flawlessly using a mathematically tracked, mistake-proof assembly line.
But before this design is certified ASIL D and allowed to be mass-produced for you, the listener, it has to survive the validation phase, the DVP&R.
Design verification plan and report. This is basically the validation torture chamber.
It really is. This isn't about normal wear and tear. This is multi-physics coupling limit testing. They stack worst-case scenarios on top of each other to push the components far beyond what any normal driver would ever experience.
We start with the LV214 SG4 standard test.
This test validates the mechanical and electrical resilience of the connectors and the encoder housing. They strap the fully assembled components to a high-frequency vibration table.
Okay.
And they blast it with a random vibration profile, generating an immense 35 meters per second squared of acceleration force.
That equates to roughly 3.5 Gs of constant, violent, high-frequency shaking. And they maintain that continuous stress for 500 uninterrupted hours.
But they don't just shake it. While it's vibrating, they subject the chamber to rapid thermal shock cycling, swinging from -40 to positive 150 degrees Celsius.
So they are inducing severe thermal expansion fatigue while simultaneously ripping at the molecular structure with G-forces.
The acceptance criteria after those 500 hours are just brutal. The contact resistance of the connector pins cannot increase by more than 1.2 million ohms from their baseline state.
Wow.
The monitoring equipment must verify that there were 0 signal dropouts lasting longer than 1 microsecond during the entire 500-hour ordeal.
Not a single microsecond lost.
And physical inspection must reveal absolutely no microcracks in the optical glass and 0 thermal demagnetization of the magnetic targets.
That proves the raw hardware can survive hell. But how do you physically validate the software? How do you prove that the 60 millisecond Dewar checker reaction time and mathematical MRAS observer actually work in the real world?
For that, they use hardware-on-the-loop, or HIL, testing.
That's HIL testing.
Yeah, they mount the physical motor on a massive dynamometer. First, they push the motor to extreme heat, saturating the iron core, the stator, and the rotor magnets, pushing the electrical characteristics to their absolute nonlinear limits.
Right, because magnetic permeability drops as temperature rises, meaning the mathematical models in the software have to work significantly harder to estimate the magnetic flux accurately.
Once the motor is thermally saturated, the dynamometer injects a violent, simulated load acceleration of 20,000 RPM per second squared.
Wait, injecting a 20,000 RPM per second squared acceleration while the motor is already overheating sounds like you're actively trying to blow up the lab. Why test so far beyond what a car will ever actually do on the road?
Because you have to know the absolute breaking point. The motor is screaming under maximum torque demand and maximum acceleration. And at that exact moment of peak dynamic stress, the engineers literally sever the physical hardware wire for the encoder.
They cut the cord while it is maxed out.
Yes. If the software observer model is slightly off because of the heat saturation, or if the 5-millisecond transition into the soft fallback sensorless control takes a millisecond too long, the motor will instantly lose sync.
Resulting in massive torque ripple or a complete stall.
But the testing criteria mandate success. The high-speed telemetry must prove that the transition was seamless, keeping the torque ripple under 5 Newton meters, and the negative sequence current ratio, which indicates an imbalance in the three-phase power under 3%.
It proves the math holds up when the physical world disappears.
And they run an even more aggressive test to validate the hard fallback, the stepwise active short circuit.
Right. They run the motor on the dynamometer at an absolute maximum speed of 12,000 RPM under full load. At that speed, the back EMF potential is massive. If the inverter disconnects, that voltage will instantly spike and destroy the electronics.
To trigger the system, they artificially inject a massive software error, specifically a sudden 180-degree angle jump, simulating a complete hallucination of the positional data.
And using high-speed oscilloscopes, the engineers track the microsecond timing of the safety net. They prove that the Dewar checker flags the 180-degree error.
The 3-millisecond debounce window confirms it.
The fallback matrix recognizes the 12,000 RPM speed is too high for sensorless control.
And the system executes the 1.5-millisecond two-phase short circuit, followed by the 3-phase short circuit.
And the critical proof is watching the oscilloscope trace of the DC bus voltage. It must smoothly decelerate the motor while guaranteeing the voltage spike never crosses the 720-volt destruction threshold.
They force the catastrophic failure just to watch the safety net deploy at the speed of light. The DVP&R is the crucible. It guarantees that the ASIL D standard is not just a theoretical badge, but a physical, verified reality.
Okay, let's just take a breath and recap the sheer scale of the engineering we just unpacked.
It's a lot.
It is. We started by looking at microscopic cracks in glass and the coefficient of thermal expansion. We analyzed the wide band gap of silicon carbide transistors and how high GVDT switching creates common mode noise that punches through parasitic capacitance.
We looked at digital metastability caused by unsynced oscillators.
And the chemistry of fretting where oxidizing tin and copper. We moved to hyperfast, heterogeneous software, where a Dewar running field-oriented control is constantly audited by a checker running a model reference adaptive system, resolving conflicts with second-order extrapolation in a 3-millisecond window.
We explored the unyielding design rules, too. Zero thermal drift, Class 1 C0G capacitors, ham-encoded ECC memory fighting off cosmic rays, and 360-degree shielded backshells.
We navigated an assembly line straight out of a sci-fi movie, utilizing UV fluorescent fluorosilicone grease, dynamic force displacement crimp monitoring, and end-of-line back EMF calibration locked down by a cloud-based MES.
And finally, we ended in the validation torture chamber, watching motors survive 500 hours of 3.5 G vibration and perfectly executing microsecond short circuits at 12,000 RPM.
It is a monumental engineering effort, entirely focused on a single philosophy, ensuring that no single point of failure, whether it is physical wear, electrical interference, or a stray neutron from space, can ever compromise the safety of the vehicle or the driver.
And I want to leave you, the listener, with a final fascinating detail from the very end of our source material.
Oh, the Python simulation.
Yes. Before engineers even build the physical prototypes we just talked about testing on the dynamometer, they're utilizing advanced Python simulation tools. They construct a massive electromagnetic transient model of the motor system.
This allows them to simulate the exact microsecond impact of a pulse loss on the dynamic thermal stresses of the system in a purely virtual space.
They can mathematically optimize the precise length of that 3-millisecond debounce window or the 1.5 millisecond phase 1 short circuit before a single piece of metal is ever cut.
The physical testing is simply verifying what the mathematical simulation has already proven, which raises an amazing question for the future of engineering.
What's that?
Well, as these electromagnetic transient models become more sophisticated, will this extreme physical limit testing eventually be reduced? Will the ASIL D standards of tomorrow rely entirely on flawless, godlike digital twins, simulating millions of lifetimes of structural fatigue and electrical failure at the speed of light?
It is definitely something to think about.
Thank you for joining us on this incredibly deep dive into the architecture of safety. The next time you press the accelerator in an EV, Just remember, beneath that smooth, quiet ride, millions of lines of code, perfectly synced hardware clocks, and meticulously greased 360-degree shielded components are continuously calculating, verifying, and adjusting in milliseconds to keep you moving forward safely.
Usually when we talk about a computer program, we expect it to exist in a perfect, abstract digital world.
But here, the engineers have built mathematical precision right into the very chaotic, vibrating, superheated reality of the physical world. Until next time.